So the first thing I am going to do is I'm going to share my screen. So can everybody see my slides?
Yes.
Right now in the,
Yes.
okay, that's good.
So one more note, excuse me, Foula. After every seminar, in the diiP web page, in the seminars page, we will also include the links for the material, the slides, the Jupyter notebooks, etc. So if you do not get the link, you can always go back to the seminar announcement on the diiP web page, and the links for the material will be there.
Thank you, Semi. So for this first seminar, we decided to give an overview of what is data science, not trying to convince you that our interpretation of data science is this, but for all of us to have a common understanding. And when somebody says I'm doing data science here, we'll know what they mean, and also give you a little bit of information why this field started, what it means, what it entails, what are the tools out there, what are the algorithms. And for other seminars, they will be a little bit more technical in the sense that we'll actually get into specific tasks or specific techniques. Okay. And as I said, I'll try to explain to you what's the field of data science, more in what it does, as opposed to try to give you a definition of data science. I will try to explain when you have a data science problem or data science project, what is the usual workflow, high-level workflow. I will talk a little bit about tools for data science, a little bit biased towards Python, only because it is so commonly used for most of the fields, and also because a lot of it has a lot of tools for this. Like even if something has not been created by Python, in Python it's usually a wrapper for that. I'll give you examples of applications where a lot of data science work. And what are the challenges that people that work in data science face? And then we'll go on the hands-on data science example. Okay. So data science is a field on an area of study which tries to use data in order to, it tries to mine things, hidden patterns in the data. And in the process, it's using different methods, scientific methods, algorithms from computer science, and processes from a project manager that is needed in order to be able to formalize and explain the findings. And at times, it can also predict unseen facts or events. Okay. So usually the data that we see in data science are large. Usually, it's not always the case. Data science, one of the main things is that it tries to extract knowledge from both structured and unstructured data. What it means here is that usually when we do analysis of data, we usually think of a table that has some columns, and each column is some variable that we understand, and we try to find the relationships between these variables. And this is what I would call a structure data, but data science does not assume that. Like the data can be raw text, it can be signals, it can be images, it can be video, it can be anything. And in order to be able to extract this knowledge from all these kinds of data, it's using techniques and tools from different fields: mathematics, statistics, machine learning, computer science, data analysis, and so on and so forth. So why data science emerged? Well, the short response is because data is one of the most important feature in every organization. Organization can be a university, it can be a company, it can be anything. And why is that? Because it enables making decisions based on facts. Usually, of course, you ask me what is data, and I'm going to tell you it is any fact, any real fact that's produced in an organization. So it's a very general thing. So if you have that, your facts, and you can identify, analyze, and mine them and get information out of this, then this enables you making a more informed decisions as opposed to using, for example, intuition or even experience. The other thing is exactly what I said before, is that the data formats and the sizes of the data, the data are exploding. That we see every day different formats come out, the sizes become even larger. So a new field that could handle these things, that would not make any decisions of how the data look like or even what they mean, had to go emerged. And this new field is not entirely new, like it's a kind of an integrated and interdisciplinary field that is using techniques and methods from many different other fields, like artificial intelligence, visualization, data engineering, and so on and so forth. Okay. Now, so examples of data science components, I would say here, is the main things that we see usually in data science is the backgrounds, basically, I would say, is computer science, mathematics, machine learning, and one thing that is very important, if there is domain expertise. Because one of the things about data science is that it doesn't make any assumptions about the data. So when you go to, you can use the same algorithm to make a prediction for, say, in the medical field, and exactly the same algorithm to do a prediction in retail. But these two fields are completely different, and the data and the semantics that they create are completely different. So a lot of times, this domain expertise is needed in order to clarify things or in order to interpret things. So in detail, usually the data science components is data engineering, because we work with such large data and so diverse data, people with hands-on experience and to be able to acquire this data, store, retrieve, transform, clean this data are very important. Statistics, because it enables us to collect and analyze large amounts of usually numerical data. Visualization, because it enables us to access and inspect large amount of data. When you have gigabytes or terabytes of data, just having them and looking them as in a spreadsheet probably won't tell you anything. It probably won't even load on your computer. But if you can have a meaningful visualization, you might actually get some idea of what this data is about or get some insight. And as I explained, also the data expertise. The other thing, which is it's usually the backbone. It's said that the backbone is machine learning and artificial intelligence, because data science is usually using models from machine learning or artificial intelligence in order to make these predictions, in order to identify these hidden patterns in the data. Mathematics is usually needed when somebody wants to understand the inner workings of the techniques. And it's usually a good idea not to use a model, like an algorithm or a technique, and just use it as a black box, because then we become, this black box can give us anything. And usually this models is just a mathematical formulation. So for every input, it will give you an output. The problem is whether this makes sense, or if it's what we're getting is junk. Okay, so understanding why or why you get what you got, or what is the process of getting what you got, is sometimes important. And of course, advanced computing, because all these models with all this large amount of data, they're very resource computation memory intensive. So skills in advanced computing become more and more essential. Okay, so when I say the data science workflow, what I mean here is that when we start a data science project, what are the usual steps that we get? And the reason I like this image is not because of the fancy shapes or colors, because what it shows you is that the process is not linear. It's really cyclical. Like you start with something, and depending on what you get, you go back, you revise it, and so on and so forth. And we'll go through all of these different steps. Okay. But this image here is really important to that, is that there is no such thing as I do that, and then I do that. My next step is that, and I'm done. Okay. It could be, like if somebody is very lucky or very smart and lucky, a linear process can. Okay, so having a data science project, the first one usually starts with a real world problem. Somebody comes up and says, I want to solve this problem. And this problem formulation can be a lot of things. It can be as ambiguous, as fuzzy as analyze my data. Or it could be as specific as please get BERT, which is one of an NLP, natural language processing, very state-of-the-art models, and try to do something with that, or use that in order to do translation. Or it could be something like, I would like to use some advanced analytics in order to help me with my image processing. Okay, again, the organization has images and it tries to see whether it can use some of these techniques. So having this problem, this real world problem, the first thing we have to do is understand what's the problem, and then identify if and there are any machine or AI problems that if we solve them, then we'll get the solution, or will help getting the solution to the real world problem. And the other one is, because we're working with data sciences, to see what kind of data we have. What kind of data is available to us, what kind of data they exist inside the organization, or we can collect from external sources. The next step, it's not exact, as I said, linear, but there is some kind of a sequential thing, is that once we understand the problem, to see how to actually get the data. And this is a big problem, because getting the data, acquiring the data, is usually a very hard process, because the data can be in data sources where you need to create specific wrappers, which means like computer software programs in order to mine them. There might be constraints on the data. For example, they might be sensitive data, in which case you'll have to start anonymize them. They might be data that come from HTML pages, in which case you want to do a lot of pre-processing in order to find the specific task that text. Like, for example, you get a large web page and you only need a couple of paragraphs there. So this is a big technical task to do. The next one is, once you have, and then is where to put this data. So the more data you have, the bigger your problem is. Can I have them stored somewhere centrally? Should I leave some of them in their data sources and have some way of communicating to that? Also, if I have data that they are connected, for example, I have two databases or two data sources. One is about the employees of a university, and the other is about the students. Like this case, the students of a university, and about the courses of the university. So these ones might have some correspondence. You might need to find this correspondence. Otherwise, you'll end up with gaps in your data, redundant data, or a conflicting data. Okay. So once you have that, the next thing you do all these things is to do what's called data preparation. These two steps, they're usually interrelated, but I have them here more of for clarity. So in the data preparation, the important thing is what is called data cleaning. Try to see how, first of all, to quantify how good your data is. Because one of the things here, as I told you, is that these models, these techniques, for anything you give them, it will give you something. They will never say, oh, I don't know what to do about them, or this is bad data. They will do something. So it's your responsibility to be able to quantify how good your data, what is the quality of your data, and what are the steps that you can do to improve this quality. And also to do what's called data transformations, because data transformations could be things, would be needed, for example, when your different components, say your different software components, they expect your data in different formats. For example, the data comes from a database, but your a machine learning model, it needs it in a CSV file. That's a very small very easy transformation, but that's what I mean about transformation. Or it could be something like your model or your algorithm assumes that your data is in a particular range, 0 to 1, but your data are not there, so you need to transform them. The next thing is once you have the data and you have them in some format that it's closer to what you're going to, the modeling task that you're going to do, is to explore this data, to see, first of all, to understand what information is contained at what level, and also to test whether specific assumptions are met. For example, you want to use a multivariate technique. Says that I decide to analyze my data. I'm going to do regression. It doesn't matter what's regression. Regression is you have some data and produce a continuous variable, but it also makes some assumptions. For example, that this data, they should be independent, statistically independent. So that's where, in this case, this step, you check whether these assumptions are met. Okay. So in the exploratory data analysis, you try to understand your data, what they mean, what are the constraints that you have, and also what are their features. Once you have that, as we said in the discovery phase, you also identified which problems, machine learning or AI problems, you probably want to solve. And if you solve, it will give you the solution, or will help you get the solution to the real world problem. So the model building is where you start building this model. Or models, depending. And there you'll see that you might need to do further data transformations. Again, when you start building the models, you'll identify things that you haven't thought before, more technical things. Model building also is that to test your model. Say I'm doing a prediction model and I want to see how good it is. So this is part of the testing. Model building also, is it practical to use this model? For example, I have a really, really good model, MCMC, say, a Bayesian model, that takes 20 days to train. That's a number which is not completely unheard of for an MCMC. That might not be practical for you, in which case you might need to change the model, or you might need to see whether you can do something to what is called to scale the model, or to enhance the performance of the model. Okay. The other thing also is that, I want to do this model, but I don't have the resources. Like my model needs 120 gigabytes of memory, but I only have 64. So these constraints also come here in the model building. Once you have done that and you found a model and you're relatively happy with the results, the next thing means what you need to do is that you need to communicate the results to the people, to your, what I call clients, is the people that they will make the decisions. In the university, it could be, for example, your PI, principal investigator, the scientist that is doing the work. In a company, it could be the manager that needs this prediction. And this is an art by itself, because you go from something which is very technical and probably very specific, and you know what it means, for example, a number that tells you how accurate your model is, to a person that might not even understand numbers. For example, your manager could be a business MBA person. understands his business very well, but telling him that your model is 99% accurate doesn't mean anything to him. So that's where communicate the results is important. So in this case, you might actually need to translate what you see there to something else. And sometimes also it's required what I call the model operationalization, which is the deployment of the model. Sometimes you create one model and send one off in order, or it's what is called batch, like whenever you need to use the model, you feed it the data, you produce the result, you get it, you analyze the result. But that's not the only environments that a model can be used, or a machine learning model can be used. It could be that you want a model that every week it predicts the next week's demand, for example, in a retailer. So in this case, you have to deploy the model to integrate this model into the organization's infrastructure, where automatically the model will be getting input, will be operating, producing output, sending the output to the next or downstream software modules or people. So before I want to ask any questions so far. Everybody can follow these things? I'll stop here. Okay, I don't see. So I assume that everybody is happy. Okay. Okay, so that's the workflow. Now, before continue, just want to go back here is that, as I said, one of the things is that you start discussing the real world problem, and you want from the real world problem to identify what is the machine learning problem, and it could be multiple ones. And here this slide is just saying that it gives you a small mapping of, if you hear some specific requests, what are the applicable algorithms. It's not very important because they're not only that. Like, for example, sometimes you say, I want to identify, for example, whether an image is an image of a cat or a dog. That is probably what we call a classification task. Okay. Now, as I said, in order to be able to do your work, data science work, and do it fast, you want to use as much help as possible, because you are building complicated things, so technically complicated things, not only analytically, mathematically, and mentally complicated things. So the more tools one has in their pocket, the easier their work is. And there are some, well, I could even say for every task there is a tool, and this is what is called, it is a good and a bad thing. It's a good thing because there is a specialization on the tool. So for example, I really think that it's a good thing that if there is a tool that's specialized for something and it's optimized for that, and you know, and you can use it, and you integrate, it makes your work easier. But with so much proliferation, it's impossible to know all of them, and also it's impossible to identify them, or hard to identify. On the other hand, there are some frameworks here, and that's the ones I have here, which they're kind of accepted or popular or effective on doing data science. One of them is what we call Python, and it is with a programming language, and it has a whole family of tools built around it for data science. Another one is R, which is very common in sciences, and the amount of tools in these two frameworks is very comparable. Another one for is MATLAB. If somebody knows how to use MATLAB, and for the things that MATLAB is good at, it is very, very efficient and very, very effective. On the other hand, one is usually constrained on this particular environment, and so on and so forth. Okay. So applications of data science, it's a very incomplete list, because basically you can apply data science anywhere you have an analytics problem, right? But what I have here is either popular or fields where data science has been quite successful, or it has enabled the field. For example, one of them is recommendation systems. It is basically a field that was created because it can exist because of data science. Basically, everything around recommendations systems is data science. And what is recommendation systems that you probably seen? They're used everywhere. For example, Facebook to suggest new friends, Netflix, YouTube to suggest interesting videos for you, Amazon or other retailers to suggest new products for you. Here, the first ones, except from this marketing, also one thing about the recommendation system is also what we call a different form of navigation. For example, say that I am a user and I want to use to explore the web. It's a huge thing. So what do we have in our in order to be able to do that? Usually we use search engines, but for the search engine to work, you have to know what you are looking. You have to know the question, but sometimes that's not the case. Like, you don't exactly know what you don't know, and that's what is called the navigation research. And these recommendation systems enable that. Okay. Data science also is starting to be used in healthcare. For example, we see a lot of examples of medical image analysis using data science, in drug development, in genetics and genomics, and more and more hospitals, at least in US that I've been, they use like virtual assistants, where you see that kind of streamline some of these processes. Okay. Fraud and risk detection was probably of the first fields. Like, one of the first email algorithms was email detection, whether it's spam or not, and it's still used extensively. In internet search, where, for example, a lot of search engines start using NLP for better quality results. People can ask right now, when was Leonardo da Vinci born? And the search engine can give this answer. Or who is the CEO of somebody, and the search engine can answer that. Question answer, name the entity, resolution, image search, and so on and so forth. In knowledge bases, here is structures where it's kind of network or graph structure, where it tries to integrate the different knowledge. For example, we have entities or real world facts, and they have relationships between them. For example, students get grades, or students are happy when it's vacation. All these different concepts, they're trying now to be integrated or to be represented by these knowledge bases. And machine learning and AI is helping in creating these knowledge bases, because you understand that in order to be able to identify all this information, there is a lot of sources to ask, and also integrate, and also to infer things. Like, how do you infer that somebody is happy? It might not be written somewhere, right? In image processing and video and speech processing, like, we've seen a lot image classification or facial recognition, or all these filters that people are using in social media. All these are parts of data science, of using deep learning in particular. Other areas which are not that known, but they have been very successful, is in airline route planning, where predictions of flight delays are used. So this is used more and more, because flight delays create a lot of dissatisfaction, but also a lot of lost profits. Airlines are, if they delay, they get charged. In targeted advertising, before people were, advertisers were trying to segment their customers in 1, 2, 3, 10 different groups. and create advertising for them. Right now, with data science, the advertising can be tailored to specific things, to specific people. I don't know whether this is good or bad, but it is possible. Gaming, augmented reality, robotics, and as also self-driving cars that we hear more and more. Okay. Now, so it seems like data science is a very interesting field, and it has potential to affect positively a lot of lives, but there are also some challenges that that are faced, and they have to be solved in order for data science to succeed. One of them is data issues. As we said, actually, I repeat that here. The data, the sizes are large, the data formats are exploding. So this becomes a challenge, like in a field where data is the bread and butter, being able to handle the data with all these complexities, it is necessary and also a challenge. And the other one is lack of domain expertise. As I explained, usually, sometimes domain expertise is very important, but also it is it's very hard to find. Like a lot of people say that the most valuable or the most expensive resource is the human expert, and although this is a challenge because in data science, and the data scientist is a general field, like it is applied, as we saw, in many different fields. So the data scientist, or the person who practices data science, cannot know all the fields. So having a domain expert is important and challenge to find. Explaining the data science to no experts is difficult because, as I said, the data science is a numerical field. In the end, what you see is numbers. You play with numbers, and you quantify things. But not everybody understands this language, and and it's not always easy to go from numbers to something else that people understand. For example, I don't know, like a model that is very successful in predicting some forms of cancer to better vitality, for example. So we have to find mappings for that. So the other thing is data science. This is actually a challenge that has been created because of misconceptions, but also part of the success of data science. People think that we can use data science for anything. So a lot of times data science go to an organization or a company, and they tell you, okay, here's the data, do the data science. That's a big challenge, because that doesn't mean anything, basically, do the data science. So this is a challenge that people who practice it have to overcome. And the other thing is that when the other part is where you don't really have data, and you have needs for data science, but you don't have a data science team, or you don't have a data science, because although there are more and more data science produced, as you said, it's a disciplinary team, a field. So it's a good data science is hard to create, or hard to, I wouldn't say produce, like to come up with all this expertise. So these people are like they're hard to find, or they're expensive to find. So this creates a challenge for the companies that they want to use, or the organizations they want to use, but they don't have access there. Or it could be that it's a field that it doesn't produce data science. For example, say that I work in a social science. It doesn't really produce any data science. So where to find the data science from? Okay. Here is, again, the challenges. A survey of what people think the challenge of data science is. You can look at it. Some of them are, I already mentioned some I don't really agree, but it is there. Okay. Now, again, I will stop here for a little while, ask if you have any questions. And for the last part of the talk, I'll stop a little bit. I am actually going to show you an example of this workflow, because I gave you all these steps in a high level, but what do they mean? So we'll get a specific example. It's kind of made up because it's very simple. We'll see how data sciences is applied there. Any questions before I go back, continue? Okay, I don't see. So let me see if there is any in the talk. No. So I continue here. So I'll start with a problem. As I said, it's a made up, like it is real world. It has some real world aspects, but it is made up, like it's toned down, and also it makes some assumptions. So I say that I work with a collaborator, and he works in medical image analysis, and he puts the question is, can we leverage ML and AI to support my work, medical image analysis? So that's the question is posing. Okay, as we first thing we have to do is, okay, let's see, what does this mean? What is this problem? How can we solve it? And how can we use machine learning or artificial intelligence on analytics to solve it? How to go about it? We ask questions is, what are the major imaging techniques that are you using? What are the major tasks that you try to solve with medical image analysis? For example, it could be that, I detect some diverse conditions. And what the things we should prioritize? Like, for example, if we come up with a list of tasks that we can use machine learning, data science, and artificial intelligence to solve, which ones we should start with? So say that we came up with, okay, how about we use machine learning techniques or AI techniques in order to get some images, relevant images, and we try to detect tumors there. Okay. So that's where we identify some machine learning AI tasks. We can even make specialize it if more. Do we want to identify tumors in MRI images? Do we want to detect whether the tumor is malignant or benign? Other questions that you can answer in order to specify your problem more. Okay. Say that we decided, what I want to do is I want to identify regions in my image that with high probabilities about tumors. Now, this identification of regions, I will call it image segmentation. It means that I will find the regions in the image that I think with high probability it describes a tumor. Okay, so where do we get these images? Where do we get our data from? Assume here is that, the images, these MRI images, we store them in a particular system, the PACS, and I will also have an SQL database that keeps another information, for example, the patient, some clinical information about the data, the patient. And so this is the two data sources where you can get information for your problem. Okay. Once we know the data sources, these two data sources that we have, is the question that we should ask is, how do we extract these images from these PACS system? What formats should we store the data in order to perform the analysis? Like these images are in PNG format, is in some other proprietary format that we need to be able to handle. And do we need to anonymize the data? Like if we're going to use, instead of except from the images, for example, we use that in order to do some downstream analysis using the patient's clinical data. Do we need to anonymize this? Do we need to anonymize who is who? Okay. So in the data preparation, once you get the data, is, as we said, one is data cleaning. Here it could be that some images are corrupted or they're bad quality. Some images is irrelevant, like yes, my storage, my system is about images, but it might have brain images, but not have a non-brain image. So we will need to remove them. We need to maybe need to transform the data. For example, if not all the images are of the same size, and we need to resize them to make them have the same size, we have to do that, and verify that all the necessary information exists in the input data. So for example, if we are going to do image segmentation, we need to have what is called examples and to train the model, like where do we have images where we can see where the tumor is. We will call that the image annotation. Like in the image, we have an annotation that defines the region where the tumor is. And we'll use that as our example in when we train the model. Okay, so the model sees, oh, how do that tumor looks like? Okay. In exploratory data analysis, here it could be what we want to see is that how do this, first of all, if you're not an expert on tumors, how do these images look like? One thing is like to visualize these images. For example, you identify that they look like this. So one thing you can see, even if you're not expert, is that depending on their direction, they look very, very different. So that might actually give you some hints on what do I need to do in order to train the model effectively. For example, it could be that you understand that if I only use images with sagittal view, then the model might not be able to identify. It will always be able, it will probably be able to identify this view, but some other view, for example, the axial view, might not be able to identify. So an answer could be that I use different views as examples, or it could be something else. In our case, in our model, we decided that, okay, so I'm going to build separate models for the different angles, assuming that I have a way to identify, to know the angle of the image, for example, is part of the metadata. Part of the model building also is that to generate the input. This is what we were calling the transformations in order to be able to get from the format that we got from the PAC system to the input that a model understands. And here we have a specific model, I call it the LinkNet. It is a real, actually, a system, a model for image segmentation, and it assumes that the data have a particular format. So that's where we do this transformation. The next thing is to be able to create what we call the training data set, is the data, the set of data that we will give to the model as examples, and also keep some of this this data in order to test how good the model is in examples that it hasn't seen. That we'll call the test images. Okay, so once we have that, we train this LinkNet, and we also specify something. How do we know whether the model is good? Okay, so we have to define a measure, a quantifiable measure, a number or a group of numbers that tell us something. Okay, so as it is common in segmentation, we'll use what is called the diiP score. It doesn't matter what it is, which says how good the segmentation is. And a larger score, it means that the segmentation is better. So we get a diiP score of 0.79 on the test images, the images that we said we are not going to give it to the model when we train it, but we'll just use it in order to see how good it is. Okay. Next step is, okay, how do we communicate these results? So we got the model, we know that its diiP score is 0.79, and now we need to go to the physician and convince him that this is a good one. This is a good model, okay. So that's where the communication starts. We can try to explain what the diiP score is if the person is has a background to understand. Give some more detailed accuracy numbers for the fusion matrix components of the dice score, or we try to visualize some segmented images, examples of successful or unsuccessful segmentation discussed with the physician. So this is part of the communications. We started from a analytical model for a mathematical model, and now we need to go to something that the other person of a different field understands. And here we finished, because remember, we just said we didn't say that we want to add this model as part of a particular system. So that's where this process would finish. And that will actually conclude the presentation. And before going to the example, so for the example I have, it was difficult for me to decide because it was this high level description of data science. So what I decided is that we'll play with a little bit some data images and also see an example of an interesting model, like how it works. But before going there, I propose, first of all, we take a 2-minute break so I can actually take some water. And if you have any questions, can see if there is on the chat something. I will stop sharing. See if
I got a question. I put it in the chat.
Yes. So as I couldn't see the text, chat. That's why I said let's shout. How do you do?
I'm sorry. Yeah. It's what happens if you don't have a training data set.
So your problem is defined differently then.
Okay.
So you have to define it that, you know, I want to do that, but I don't have a training. I don't have, for example, examples of tumor.
Exactly. For example, I can take your problem of cancer tumor. You have a set of image, and yes, on this image, there is cancer cells and non-cancer cells, but you're not able yet, or the physician is not able yet to tell you that is a tumors and that is not a tumors. But yet you have two different kind of tissues. Do you have a way to, and you don't have a training data set because you cannot show what is normal tissues and what is a cancer tissues.
Right. Yes, so first of all, you define the problem differently, as we said, right? It is that I know the problem, I want to do this segmentation, but I don't have this training data. And yes, there are some techniques, and there is more research work also working on what happens if you don't have data or you don't have enough data to do that. Okay, so there are techniques to do that. Yeah. Okay. Now, how good it is again, you have you do an investigation on a background research or bibliography, identify a couple of techniques. You start deciding which ones you'll try. You try a couple of them to see who ones they work. You might actually need to do some ground work in order to fill in the gaps, because you might find something relevant, but not exactly. All these parties of the work of the data science.
Then you have to build a training data set anyway.
You want to, you don't necessarily want to build a training data set. You want to build something that will enable your model to predict the tumor.
Okay. Okay. A model, it's not necessarily a data set. That if you have a good model and you can explain it, it's okay.
For example, it could be that I don't have a model, but I have a system that it is, I'll give you a set of rules, like the 80s expert systems. Okay. That it gives you the answer.
Yeah, I can tell you perhaps make a choice between the small cells and the big cells.
Exactly. Yes. But of course, in 2021 there are other techniques. But I'm giving you an example that it's not always your issue to create a data set, a training data set.
Yeah. Okay. Thank you.
Very good question. Thank you for this question. Anybody has any other questions before we continue? Now, as I said, I'll take a 1-minute break. Yes.
Yes, thank you for a nice talk. I just wondered, you talked about data segmentation in your example, because only a part of the image had the information about the tumor. How do you code your model in the training data set to know where to look, where the area of interest lies?
Okay, so you're going to a lot of different issues, actually. First of all, I didn't even explain how you represent this image. The image, we show an image, but in the computer, it's not an image, it's something else. It's a different data structure. For example, it could be a grid, right? And it could be a grid with very small cells, what we call the pixels. Okay, so as part, if you have training, what you want to do ideally is that you go and find all these little cells and say which ones of them they correspond to cancerous parts in the image, and which ones they are to parts of the image that's tumor, and which parts of that's the ideal. You don't have that. Maybe you can do other approximations, but that's an example of how you would give this data, but this information to the model. Again,
okay, so you couple the spatial information and the image, so you can do it on scale, so you can do it on a pixel basis, but you do give a list of where to look to the code.
As I said, the ideal case is this, is where you, what we call where you have training data, where you have examples. Yes, but this, as you understand, is a very hard problem. Like if the physician takes, say, 5 minutes to do it per MRI image, we probably won't have enough data, especially if these models need, say, hundreds or thousands of such examples. So you go to different techniques. Okay.
Thank you.
But that's the ideal case, is that if you can give examples to the model, and the model learns what are the signals in these examples that predict what you want to predict. But that's not the only what is called a technique in data science. This is one technique, a simple technique that I think people can understand, and I can see also issues about it. Any other question? Okay, if it's okay, can we take just 2-minute break, and we reconvene at like 5 o'clock, or if you want more, but I think if we can just start at 5 o'clock, it's fine. Okay, I don't see any objections, so I'll stop the record. Well, I'll leave the recording here, and I'll be back at exactly 5 p.m. In 1 minute, we'll start. Okay, so is everybody ready to start? Should we wait a little bit more? Okay, so as I said, in this part of the seminar, we have some hands-on examples, and in the other seminars there will be more focus, because we'll take a technique or a set of techniques and we'll describe them, and so we'll have examples for that. But here it was a general overview, so it was hard to find an example, what would be a representative example. So what I decided is that we'll get some examples of some data analysis or inspection, and coincidentally, I'm actually going to use images. Let's see, how do we inspect images? How do they look in the computer? And then we'll see an example of a training model, a deep learning, a machine learning AI model in practice. How does what input you can give, and what it can predict. Okay, and I decided to use segmentation model, what we call as instance segmentation. Explain what is this, only because it was relevant to what we discussed here in the process, and also because I think it's a very, it shows the power, it's a quite powerful model, so what can be done later. Okay. So for that, I am going to start sharing a different thing, which is what we call, and now we are going to actually see a little bit of code. We don't need to understand a lot. I give very few example directions what this means, and then you can play with that. And I'll give you all the information how you can set up the code and where to get the data or anything in order to be able to run. So say that we want to do, so we have some images and we want to use a particular model to do what is called the instance segmentation. Segmentation, we already said that it is to identify specific parts of the image that show something, okay, specific regions of the image. The instance segmentation, it also tries to identify what kinds of objects they are. So for example, in the image that I have here, the instance segmentation will identify the regions where, this is donuts if you cannot see, so they will identify the regions where the donuts are, but they will also, it will also find the object of the donut that will say, this is a donut, this is a knife that we have here, and anything else that we have, we'll see. Okay, so so we get the image. First thing is we load the image. In order to load the image, we have to have a file. This one here, donuts.png, is the file in the file system that has information, and we use a particular software that is called here image.io, a library that can load the image, it can process the image, it understands the information in that file, and it can, among others, visualize the image. Okay, so we might want to see some basic properties of this image. For example, what kind of the image it is, what is the structure. What we mentioned here is the structure is the internal format that the computer understands. Is what I told you. Like we see an image which is it has objects, has colors, it has scenery, it has background, but that's not what the computer sees. The computer might see, as I said, a grid structure with many tiny cells. Okay, that's what we see here. So this program sees a structure which is called an array. We can assume that is like it is this grid. It also says that the size of the grid, this grid that we'll say, this grid structure is 316 by 503, by 505, and it's also a 3D structure. That means it also has another dimension, and this is what we call the color dimension, because these are color images. So in computer science, one of the formats for these images to understand is these different, excuse me, channels. Which one is the ARC channel, the blue channel, and the RGB green channel. Okay, so that's basically says here. And also we can see things like, okay, in the R channel, which encodes the R color, specific values. Okay. We can also try to see a specific channel. Here, the R channel. It doesn't look very red, but the encoding is not good on my computer. It's okay. Or you can even change the values on that channel. So I get the channel and a specific part, like here where I made it very red, I make it completely red. Okay, so this transformation, this is an example of a transformation. Or you might want to split the images in different channels. So how does it look in the different channels, the RGB that we said? Okay. Or you might want to convert it to a grayscale. This is something a lot of times you do because some of the models, they are not, they only understand grayscale images. So this is examples of transformations. And one relevant to the example, to the question that we just answered. Well, the previous question is that I want to create a mask. So, for example, I take the image and I blacken specific parts. So the ones I did is that outside of the circle, and that's where the same technique you'll use in order to create the examples that you said. If you need to create these training examples, you go and you mask this black thing that I have here, the specific parts of the image that describe something that you say, this is where the tumor is, this is where the donuts are not. Okay, something like this. So this is examples of the, we just ran that. Now once we see the image and we inspect the image, now we get a little bit more focused. Say that we want to be able to use these images in order to feed them into this model, this it's instance segmentation model. It's called Mascar CNR, and we'll see it. And we need to do some pre-processing. Okay, we load the image again. So here I use a different, let me see something. Yeah, I use a different program that understands and loads this image CV to a different library. Okay. And so the image, as we said, one of the transformations usually happens is to resize the image, because say that this image was not, we decide I'm going to use 128 by 128, but this image is a different size, so we can resize it. Okay, so you see the difference from here, I made it smaller. I can add some noise in the image. So for example, sometimes you do that in order to smooth some models, they work better when you remove some noise, this smoothing, what is called smoothing. You might want to decide that I want to normalize, is what I said, is that a lot of algorithms, they work better if they expect, or they work better if the data is in particular range. And that's what we did here, is that the original range was from 0 to 2 to 5, and we went, the normalized one is from 0 to 1. Okay. These examples of different transformations. Another thing that in these models is what in these image related models is what we call the data augmentation. And this is where you try to add, you have a particular data set, trained data, say 300 images, and you want to find a way from this to generate more images so that you have more data to give to the valid data, though, to give to your to your model. One way is to start doing different transformations, rotations, translations on the image. So one here is that, sorry, I'll get the image. I can flip the image. And one thing about this transformations is it's probably, you see, I had an image, and from the same image, I created another example, which is again a valid image. And now instead of having one training example that I'll give to the model, I have two. One thing is when you do these transformations, usually now the libraries can do them automatically, but it's a good idea to also visualize some of them, just in case you see that when you do the transformations, you don't distort some information. Okay, for example, if I was doing a transformation and somehow the knife was disappearing, so you're changing the information that's there. Okay, or you're doing something that actually cuts the image in half, so it distorts the information. Can vertically flip the image, different. So here, rotations, all these. And the good thing about image data, there are a lot of different transformations that can create. So it is a data augmentation on image data is actually a doable thing, as opposed to other data, for example, text, how you're going to generate a text that makes sense, or add some noise here. Okay. So once we do the transformations that we need, of course they look a little bit how to say, random, but they, as I explained to you, all these transformations are relevant if you're working on image processing. You'll do some of them or all of them. Okay. And now say that I want to perform this image segmentation. Now, as we said, we were going to use this masker CNN model. It's a particular deep learning AI. AI is an artificial intelligence model. It's neural network model that does exactly that, what is called this instant segmentation. We're not going to train. It's actually a very big model. And we're just going to see how once we have trained it, we give it enough data. And here the data that we give is what is called here the COCO data set, is particular benchmarking that people have already assembled. And this model, the creator or the maintainer of the model has already done the work for us. He took the model and he trained in this data set. And also, thankfully, the image that we are using here is relevant there. So we don't need to do anything else. Like taking the particular, this model trained on this data set will work on our data set, which is this single image. Okay. So this is nothing. We load this file, this model. So a model for us is basically software representation of the model. What I did is I have a software program or a software structure that describes this neural network model, and we'll see examples how we can build these models and how do they look in different seminars. Okay, we'll load these models. That's where we get the trained model. All these things just loading the already pre-trained model. Like the model that has information, knows how to get an image and segment it. Okay. Sorry, let's add that. And then we take our image. Now the donut image. And this is where we say, use the model. The model here is the same one as we have it here. When this variable basically says it is a presentation, the reference, what we call in computer science, to the model. So it's kind of a pointer. This is where this model is. And we call, sorry, where we are. We are here. So we make the prediction. Okay. You see, that's why it would actually take some time. That's why it is impractical to demonstrate training the model. Just to predict this simple image takes time. Let's see here. Sorry for the wait. It takes a little bit of time. Any questions on this while we wait? Unfortunately, because we had to do it on real time, you will have to wait a little bit. Not here it is. Any questions though? Let me see. Yeah. Let me see. So now that we visualize the results. Here it is. Sorry, it's this one. There, and you can see that it correctly identifies the donuts. And we'll see actually the label, the knife, and I think the tray also. I think this is the tray. Now we can actually visualize how it's segmented. All these are the different segmentations. Okay, and also the labels that it gave, you see, this region it identified, and actually the region that it identifies the circle. And then it added one bounding box just to say, oh, this circle that I found here belongs to this object, which is a donut, or this one here, it's a knife. Okay, and then we can see that classes, as we said, it identified a donut, a knife. Oh, okay, and so what he found here, the big border was the dining table. So basically this big red here was the dining table. And that is the demonstration. So that is basically it. If you have any questions on that or any comments, be happy to answer now.
How do you judge whether the training set is sufficient or not?
So this is what I said, that one of the parts of building the model, you define some metrics, one or two, some numbers, where it will tell you, it describes the quality of what you predict. For example, a simple one, if, for example, I want to predict demand, like I'm a retailer, and I predict how many dresses I'm going to sell this week. So an accuracy measure there, a metric could be something that it could be the difference between how many you predicted versus how many you sold. So that's one way of judging the accuracy of this, how good it is. Now, for this particular one, the segmentation is much harder. One is the dice image that I said. So coming up with good accuracy measures, these numbers or group of numbers that describe well, tells you something about the efficiency or the effectiveness of the model, is part of building the model. And sometimes if they don't exist in the literature, you have to come up with that if your model, if your problem is unique enough. But usually for specific problems that have been solved, there are different different numbers or different metrics that have been proposed or people are using. Okay. For this one, for example, here segmentation, it could be how much, what is the margin of your error? Like if you here you're trying to find a region, but you might be finding a smaller region, or you might be finding a larger region. So a number that describes this difference could be an accuracy measure. Any other question?
Yeah, we saw that you have as a result, for example, the background. The algorithm takes the background as a, as a label.
Let me actually go back and see what.
How do you handle that to avoid to take the background results as a label?
This is where you have to say, I don't even think this is a background. Well, in this case, but that's where you have to specify what is the background. Here, it's assumed that it is a table. I have the impression it's actually a table. It was right.
Okay, so you just take just the gray pixels. I mean.
No. As part of it, you can say parts of it is a background, and then it will learn what is a background, the model.
Okay.
One of the case, or it could be, as you said, yes, I'll give you some rules there. But if you can specify that's the background, then you can learn it.
Okay. So then you can classify the objects as a donut, as a diiP, as a background, because you have labels. Okay.
You see here, I think I haven't put the tray as a label, or it doesn't have, so I didn't identify the tray. You see, because there is also a tray, but I think I haven't added in the. This is the labels that it identifies. I don't think there is any tray in here. These are very interesting questions, but they're very specific to that model, the Masker CNR. One thing I want to say is that this is a specific model that for a specific problem, a different model or technique for the same problem might make different assumptions. Okay, so I can't tell you how it's solving here, and then tell you that that's the general answer. I can give you proposals how you can handle it, but I'm not saying that that's how it's handled here.
Okay, thank you.
Any other questions? Or if they're not, this is the end of my talk.
I have one other question. You say that before you have to do a data augmentation, but you say that we have a procedure to do that, which means it's not to do a random stuff with the data augmentation. So how do we do the data augmentation to, how to avoid to not randomize the data augmentation? If you want to control the data augmentation.
Sorry, I'm not sure I follow your question.
I mean, if we want to create a data augmentation, you say that it's not a good idea to randomize all the different scenarios that we could have.
No, I didn't say randomize. What I said is make so in the images there is a very good way of doing it, because an image you can translate it like an image of a dog. You can flip it and still an image of a dog. Okay. What I'm saying is that, but sometimes the images, the image itself, it can have a very strange shape. So it's good to look at some of these transformations that you do, that you don't miss some information. For example, it could be that the dog is in some specific place in the image that if you flip it, it will go away. In which case, then you create a non-valid image. That's the only thing I said.
Okay, but in general, for example, for a data set, it's a good idea to create a different set of the same image and with different transformation.
It's good to have a lot of examples. Yes.
Okay, but is there a maximum of possibilities of translations or a minimum? I mean, or it doesn't matter how many transformations I have for this image?
Well, that's a strange question. Say that we have two different images, right? And it is an image of a cat and a dog. Half of them are images of cats and half of them are images of dogs. You can start transforming the images of the dog. What you don't want to do is, for example, you end up having 1,000 images of dogs and 10 images of cats, because then you create what's called a different class imbalance. So there's no constraint on how many you're going to do, but you don't want to distort the distribution of your data that you have. Because if you have, as I told you, images of dogs, 1,000, and one image of a cat, and then you can train a model that you can always say it's a dog, and it's a very, very accurate model.
Okay.
But it's not a good model.
Yeah, I see. Okay, thank you.
But the training, the randomness of the training is really robust against rotation or simple flips, horizontal, vertical flips of the data. I'm really surprised.
I'm not sure I understand the question. Sorry, repeat.
If there is a symmetry in, like your donut example, if you just flip it horizontally or vertically, it's basically the same matrix behind the screen in your 3D array. And so I'm surprised that the code does not recognize that it's the same image that is simply.
Yeah, it's actually, if you look at how it looks, the grid, the structure is actually two different structures. For example, say that I have only donuts, okay, and this donut, it's a grayscale image. So I have the background, which is 0. And I have the donuts, which is 1, okay? And say that I have one donut at the bottom of the image, okay? Then the internal representation will be ones at that place and zeros around it. But when you flip it, it goes as well, if I'm right, the ones on top and everything below it is the 0. So the structures that the computer sees is very different. It's two different things. That's the difference. What I said is that what you see, what the person sees, and what the computer starts. What is the format, the structure that the computer program understands? And then all these new models do is that they start with these 0 and 1s and tries to identify lines, and then tries to identify shapes, then try to find identifiers that they are no matter where they are. All this is what these models will do. Otherwise, if it was exactly the same structure, we wouldn't need a model. Like having this invariant, translation invariant structure would be all we needed, and the software, the computer would understand it. Oh, these are great questions. Any other? I'm really glad, because it seems people got engaged and they understand. Okay, if there are any no more questions, this is the end of my what I wanted to present. I am just going to stop the recording. Just